And if you're lost, please let me know. Please stop me, right? Okay, so first of all, this is a joint work with my advisor, Richard Edinburgh. Okay, let me start with a set partition. Okay, take the finite set usually from 1 to the n. For examples, I will have the 1, 2, and 3. And please divide this set into the blocks, disjoint and the non-empty blocks. So here I have the first set partition 1, 2, 3. This set partition has 3 blocks with the singletons. And the next we have the 1, 2, 3, 1, 3, 2, and 2, 3, 1. We have the 3 set partitions with the 2 blocks. And 1, 2, 3. Okay, we have the 1 block and 1 set partition. And these are the 5 set partitions. And here we may give this a partial order. I mean, you may go up, down, okay, by joining the 2 blocks. So here you joined 1, 2 here, 1, 3, and the 2, 3, and the 1, 2, 3 all together. So we say this is a partially ordered set, poset, and it has the name pi 3. Okay, and the next I will give the one more restriction here. Okay, if the block size is the even, what happened here? Okay, let me have the pi 4. Okay, because all the block sizes are even, so this number should be even number. Okay, so in this case you have the 1, 2, 3, 4, 1, 3, 2, 4, 1, 4, 2, 3. You have the 3 set partitions with the 2 blocks, and 1, 2, 3, 4. You have the 1 set partition, and you may give the partial order here. Okay, because you have the unique here minimum elements, we say this is 0 and this is 1, minimum and the maximum. Here you have the maximum, but you don't have the unique minimum elements here. So if you need, sometimes we may add the minimum elements here.
Well, why is this pi 4? I don't understand.
Pi 4, sorry, okay, so I will say here the 2. Okay, this means that we have a restriction, okay? Thank you.
So you stick to the case when every block is even?
Yes, every block size is the even. Okay, any questions so far? Okay, here we have the theorem. Okay, I want to keep these theorems. I'll be right here. Semester in 1976. The Möbius function of this partially ordered set poset with a minimum elements. I said because of these 2, we need these minimum elements, right? This is given by the -1 to the n minus first Euler numbers. Okay, so Möbius function is the -1 to the n times n minus first Euler numbers. What is the Euler numbers here? Okay, the Euler numbers means, as you know, the number of the permutations in Sn, which has these patterns, alternating patterns, up, down, up, down, up, down. Okay, and the Möbius function is defined here. Reduced Euler characteristic, the order complex P minus 1. Okay, I will define the Möbius functions like the reduced characteristic of the order complex. I know this is not the usual way we define the Möbius function, but I hope you're fine, okay? I will show you the example, okay? In this case, look at this.
So n is even, right?
Yes, n is even. I wrote that there are 2, right? Index 2.
Then is there has a meaning -1 to n?
-1 to the...
I mean, n is even.
Yeah, n is even number. It should
Yeah, so
be.
why do you have a -1 to the n? If n is even, that's always 1, right? So
Did I miss here?
N is not even. Or does n have to be even? Or it does. You're right. Yeah, it does.
Yes, you're right. Okay, so n is even, so... Okay. let me, I think there is a typo, so I don't remember exactly, so
Maybe.
n over 2, okay. So I will double check this, okay. N over 2, okay. So it was, n is even numbers, always, yeah, n over 2 is. Okay, so here, right, what is the in the case of the n is 4. In the case of the n is 4, okay. I will not use the maximum and the minimum, so don't think about this maximum and the minimum. So you have only 3 elements, right? So the order complex is just 3 points without the maximum and the minimum. Okay, you have the 3 elements, 3 points, 3, and the reduced minus 1 is 2. So in this case, the Möbius function is the 2. And how many permutations do you have with alternating patterns? N minus 1 in this case is 3. So you need the permutations with the patterns increasing and the decreasing. Can you guess how many permutations do we have? Already you have the answer? 2, right? So 1, 3, 2, increasing and the decreasing, and 2, 3, and 1, increasing and decreasing. You have only 2 permutations. Okay?
So what is criteria again? That's
Reduced characteristic of the order complex.
reduced characteristic.
Yes. And the Richard-Stanley was one of the.
What does that mean? It means alternating sum of the number of faces
Yes. So
of each dimension.
yes, plus and minus 1. So, you know, we did this in high school, add all the vertex numbers and edge numbers, minus face is 2, right? Something like that. Okay, Richard-Stanley was the one committee members for the Sylvester, and he generalized this pi n, not just to d, pi n d, okay? So this is all the partitions of the set from 1 to the n, where each block size is divisible by d. Okay, divisible by d. Okay, so here we have the theorem. Not just 2, if you have the d, here you need the number of the permutations. In S of the n minus 1, which has the patterns increasing at the first d positions, and we have the descent at every d positions.
Is the number of vertices, number of points, or number of edges?
Which number of the vertices.
Vertices.
Yes, I will show you the examples, okay? Usually, yeah, I enjoy to skip some definitions with the formula. I will show you the examples, right? In the case of the n is 9 and the d is the 3, this pattern means 1, 2, 3 down, 1, 2, 3 down, and 1, 2. Okay, I will not use the old 9 because here we have the n minus 1, so we have 8 points. And we want to count the permutations which have these patterns, okay, by using the Möbius function. But it is not easy to count the number of permutations. That's why we are using the Möbius function. Okay, whenever you want to know the numbers, you have to find the Möbius function. Any questions so far? Any question?
I was thinking of the definition of various function. Usually, when you have a poset, then you define it like.
Actually, it's the
alternating.
same thing.
Yeah, it's
Right.
right. But here it's the same. Just it's
If I talk about a little more for this D divisible, I will say this is a D divisible poset. Okay, we have the another theorem here by the Mr. Watts in 1992. Okay, this poset with the set partitions, each block size is divisible by D is EL soluble. She found this. Okay, this poset is the EL soluble. Okay, edge lexicographic soluble things here, right? I cannot explain all the things EL soluble, but this means, okay, if you have this as really nice label for your edges, 1, 2, 3, 2. Okay, this is not right now, but I mean, if you can give the good labels for the edges, okay, you may show this is the EL soluble, and you can find the order complex of this. I mean, the homotopy type of the order complex of this poset. Okay, because she found the EL soluble here, we have the corollary here. So the order complex of this poset is homotopy equivalent to the wedge of the many spheres of dimension n over d minus 2.
I don't know what is shallow.
Okay, EL shallower means, okay, there are, if you can give these some labels, okay, for the edges as I did here, right? Then, okay, EL shallow means then you can give the natural shelling for your order complex. Okay, that is the EL shallower conditions.
natural.
Oh, okay. So here, I mean, okay, you may say if you can find if you can show the poset is the EL shallower, okay, so you may say the order complex is homotopy to equivalent some wedges. Okay, so we may have the shelling for the wedges here. Especially this is really great because this is the wedge of the spheres, and all the spheres have the same dimension n over d minus 2, and the numbers of these wedges are that many means the number of permutations there. So if you find the Möbius function and you know the dimension, so you may sketch the homotopy type of your order complex clearly
The
here.
order characteristic will not change when you the same homotopy type. Right? So this tells you that you understand the topology of that complex, so you can easily compute the homotopy type, so you can easily compute how many permutations there are. Right? So that complex made or poset looks very complicated, but since you can shell it into something very simple, a wedge of spheres, you can easily compute the homotopy type, and then you can have a formula telling you how many permutations are of that.
Can I? How about the case n over d is 1 or 2?
N over d is the 1 over 1 or 2.
And then how about the dimension of
Okay, so here we have only the case is that d is greater than 1, so we don't have the case n is 1. Okay, in the case of the n is 2, okay, you may have the dimension 0. Okay, so you may have some points. Okay, you may say this is so let's use two points. Let's just so you know it's right. So we have this wedge of the fields here. Okay, and then next. I want to talk about group action here. I mean, Sn minus 1. Okay, because you have the n sets here, you may have the symmetric, I mean the group actions for the symmetric group to your sets, right? And naturally, okay, you may have the x on your order complex, okay? And we may say these group actions on the reduced homology group of this order complex. Actually, this is of some parts of the history here. However, right, the good thing is this group action is really well defined and really famous. Already we knew this. Okay. Here we have the theorem. Okay, this action is this packed module of the shape. We have the D boxes here. For the first row, you have D boxes. And the second row, you have the D boxes again. And but the final has D minus 1 boxes. Okay, so I'm sorry, okay, I cannot explain what is the spec modules in 50 minutes, right? But the important thing is this group action is well defined and it is the spec module, okay? When you talk about the dimension for the spec module, okay, the dimension for the spec module is the number of the filling the numbers from 1 to the n minus 1 into the boxes. But each row is the increasing and each column is the decreasing. But if you flip these boxes to these directions, we have these patterns, right? So it makes sense, right? So dimensions and the number of permutations. Any questions so far? Can you find the strange thing here? For your history here? Okay. We started with numbers from 1 to the n, right? But somewhere, if you see that these three conclusions, we dropped n, right? You have the n minus 1 vertices here, and you have the n minus 1 boxes here, and all the permutations for 1 to the n minus 1, right? Somewhere we dropped the n, so I will introduce the new notation here. Okay, so I will introduce the pi z. Z is the subset of the 1 to the n minus 1, and we call this, find the last block is the pointed block. And the next, the pi is the partition of the complement of z. And we say this is the pointed set partition pi n minus 1 and the dot. Okay, we need the example, all right? In the case of the n is 8, in the case of the n is 8. Okay, there we don't have the n because when you prove the some group actions or the spec module things there, always you have to fix your n as your final number. So you should fix the n as the final one. I mean, even though you have the one more box here, it should be n. So always you have to fix the n as the last one. So I will drop that. In the case the n is 8, I will use just n minus 1. I mean just a 7. Okay. So here, okay, in the case of the 1, 2, 3, 4, 7, 5, 6. Okay. So I have the set partitions of the 7 elements, right? And I will write that the final one is special, the pointed. So I will say this is the pointed block. Okay, why this is the pointed block is special? Because when you have the set partition, I told you each block should be non-empty, right? But the final one could be the empty. So this is possible. Okay, this set partition is the fine. Okay, so the final block is could be the empty, right? But don't worry about this too much because this is not a new thing. Actually, it has the same combinatorial construction for the n in 8. 1, 2, 3, 4, 7, and 5, 6. In this case, if you don't like the pointed set partition, please erase this and put the 8 here because always the final number is 8, right? So actually, pi n minus 1 point block is the same thing for the pi n, okay? But I don't want to use the fixed n and fixed n for your all the proof, so I will use the pointed set partition instead of that, okay? Any question? Okay. Now I want to generalize those 3 theorems there, but actually if you want to generalize the theorems, we need some poset, right? But it's really hard to find the poset. We have to generalize those conditions. So I need a little more structures here. But I hope you already know this. Okay? Compositions. Okay, just we need the compositions. Okay, what is compositions? Okay, positive integers where the sum is the n, right? And all your entries are positive, all right? This is a general composition. But in our case, do you remember here? The last one could be the empty. I mean the size 0. So I will give it just one more condition here. Everything is positive, but the last one could be 0. Okay, this is new compositions. Here, I'll write here. Okay, and because we did the set partitions, we will have the integer partitions. Okay, this is the last structure, okay, believe me, okay? So integer partition, okay, what is this? Okay, this is the multiset. Okay, where the sum is the n. Okay, where the sum is the n. Okay, so you have the 3 and 1 and 1. This is the integer partition for the 5 because 3 plus 1 plus 1 is 5. Okay. But here we don't have just set partition. We have pointed set partition. So I want to hear the pointed integer partition. Okay, pointed integer partition. For the 7, you may write 3, 1, 1, 2. 3, 1, 1, 2 is the integer partition for the 7, but I will point the 2 here because 2 could be 0. So 3, 1, 3, 0. This is possible for your pointed integer partition. Okay, so I wrote all the 3 structures here, the compositions and pointed integer partitions and pointed set partitions. And I will write here the function, the type, the function types. Okay, what is this? Composition. You have some entries here, positive numbers, right? You should keep the order. But if you permute the order, okay, you may have the pointed integer partition, right? So this type means just permute all the orders for your entries. But please remember the last one should be the last one because it is pointed, right? And here you have the set partitions, the blocks. If you read only size of the blocks, you may have the pointed integer partition. Okay, so this type means please read the size of each block. Okay, so you have the 2 types.
So what's the difference between the compositions and pointed integer partition? Just a matter of the ordering?
Yeah. So here you may have the 2, 1, 1, okay? But here you may have 2, 1, 1, 1, 2, 1, 1, 1, 2. Okay? Okay? And for examples, here you may have 1, 4, 2, 3. Okay? So you have the size 2, 1, 1 set partition.
Why is this 1, 1, 2 marked equal this 2, 1, 1 marked?
It's my fault. Okay, sorry. Okay, yes, you're right. The last one is the pointed, so I should keep you cannot permute the last one, okay? So keep the last one and permute only the others, okay?
But the pointed integer partition is allowed to have same number appearing many times.
It's a multi-set. Now we may have the poset. Okay, I will write here. When you have the composition, okay, pi composition means some subposet of the pointed set partitions such that there exists the composition D, which is greater than or equals to C, and type of D is type of this pi. Okay, this is our poset. This is a subposet of this.
But
Do you mean a composition bigger than a composition? It's a component by component?
Yeah, you may add the adjacent two entries if you want to go up, right? So here, let's suppose you have the C, okay? And if you add the two adjacent entries, you may go up, right? So you have these, right? And by the function type, you may have some subposet here, right? And if you image that, inverse image that, we cannot guarantee you may have the unique minimum elements, right? But this is the subposet which we want to use. Okay. I know this is a little complicated, but we need this because if you want to generalize some conditions, each block size should be divisible by D, but we don't want to use that condition. So you may have any kinds of the size of the blocks, right? But even though you have the seals, okay, you cannot go up by joining the two blocks. You need some more, and some of you may think, okay, may I have all the subposets which is greater than these C's? You cannot, okay? So you need some conditions here. You may have the pi, okay, which satisfying these conditions. The type of the D is a type of the pi.
This pi C pointed, it consists of the set partitions.
Pointed set partitions.
Consists of the pointed set partitions whose type
It's
refines down to this
yes.
C.
The block size for the pointed set partitions should be greater than the composition C.
But what is the type? Type of phi is integer partition.
Type 1, type 2, okay? So this is the type 1 and this is the type 2. Okay, is it better?
You want that these block sizes are equal
To the
and then you commute the block sizes and you want it to be bigger than
C, right. Okay. Next, I will generalize the old things here, right? Not just the divisible partition. I will use this poset, okay? And for this portion, this is vegetable spills. And the group actions, okay? We may have the same things here. But here the boxes. You have the C1 boxes here. And for the second row, C2 boxes. And the last one, you will have the CK boxes. Okay? The previous cases are your composition C is the D minus 1. Okay? So we generalize the D minus 1 to any kinds of the compositions. Any question?
No, so I don't understand. This is what? Now you have modified the theorems to the new result.
I'll write I will write the. Okay, I'll write the old things clear here.
So the Möbius function of this poset will count.
Okay, beta of C is the number of I didn't write here, the number of the permutations had patterns C1 and C2, okay? And this is a wedge of spills and the number of the okay, such numbers of permutations, spheres of dimension k minus 2 and the spec modules, and we have this C1 to the CK. These are so natural generalizations for the composition C.
Then you mean that if we fix a C vector C like that, then we have those results?
Yes.
Then how about the case C changes?
What?
If we for example, for the vector 2D, comma D, comma D, comma D, comma and D minus 1 can have then we can have
The previous theorems, you mean?
in this formulation, we can also define the vector, another vector C equals 2D, comma D, comma D, comma D minus 1. And we can also define the
Any
complex, so we can. Then how about the results remains the same, or how can it be changed when we change the vectors?
If this is 2D and D minus 1? All right, so you have the same numbers of entries, so dimensions are still k minus 2, right? But if you have the D, and D minus 1, but in this case you have the 2D and D, right? So there are the different numbers of the permutations having these patterns, right? So the number of wedges will be changed. Okay? Any question or?
So is computing better, difficult? Probably.
Yes. So you have to find the Möbius function. Okay. It's so hard to find the compute the beta C, but you may compute the Möbius function. Okay. So if you compute the Möbius function, you may know the number of the spheres for your let's see.
So this is a corollary of the main theorem. This is a theorem.
Okay. Theorem 1, theorem 2, theorem 3, I would say. This is not the corollary anymore because, okay, Möbius function, okay, this is not hard. But here, do you remember, okay, it was the corollary for the Ear-Shellover theorem. But we couldn't find the ear-shelling here. We tried a lot, but if you have this some pointed set partition, I mean, we cannot guarantee each block size is divisible by D. In this case, it was really hard to find the ear-shelling, so we just gave up. So we used the other conditions here. Okay, look at this. You have the composition and the pointed integer partition and pointed set partitions. So here, if you give the order here, you may have the composition. So if you give the order for your pointed set partitions, I will have the ordered set partitions, right? Just give the orders for your blocks. Okay, but this is not interesting at all because this is just the isomorphic to the Boolean algebra. Okay, so this is not interesting. But, however, if I have some subposet of that, for the composition C here, please define the delta C. This is the set of the OD ordered set partitions sigma so that the type of sigma is greater than equals to C. I would say this is a type 3. Okay, so if you have the C here and you have the D, okay, and if you read the size of your blocks for your ordered set partition, it should be the one of these D. Okay, so you may have the subposet of delta C here. Because this is important, okay, I will show you the example. Okay. In the case of the C equals 1, 2, 1. Let's suppose C is the 1, 2, 1. Here you have the 1, 2, 1. And I will write all the D's here. Yes, 1, 2, 1. If you add these 2, you have 3, 1. If you add these 2, you have the 1, 3. If you add these 2 entries, you have the 4, right? This is C, these are D's, right? And the next, I will count all the ordered set partitions. It has type of these, right? Okay, so here you have the 1, 2, 3, 4 numbers, okay? For this block, you may have the 4 choices, and here you have the next 3 choices, right? So 4 times 3, you have the 12 ordered set partitions here. And for this one, okay, you have 2 blocks, size is 3 and 1. So if you pick for the 1, okay, you have the 4 numbers. So you have the 4 choices here and 4 choices here. Total, you have the 8 ordered set partitions. Okay, and here you have just 1 block of size 4. So you should put all the numbers into the 1 block. So you have only 1 ordered set partition here. Okay, 12 and the 8 and the 1. If you see the 12 and the 8 and 1, you may see 12 edges and 8 vertices. Okay, so you have here the cube. Okay, so I don't have enough time, so already I gave you the pictures here. Okay, so here I gave you, okay, 8 vertices of the block size 3, 1 or 1, 3, and you have the 12 edges, okay, of the size 1, 2, 1. So you have the cube, okay? And as you know, this cube is homotopy to the wedge of the 1, 2, 3. 1, 2, 3, 4, 5 spheres, all right? We proved the order complex of this poset is homotopy to the wedge of spheres of with this condition.
Homotopy to the wedge of 5 spheres? I don't understand. You mean the graph?
Yes, cube. Cube is the order
One skeleton.
One skeleton? What is that?
One dimension.
Yeah.
The surface of a cube is a 2-sphere, right? So this is a graph.
Yeah, this is graph. You don't have the faces here.
Okay.
I mean, facet is the dimension one, not the face, okay? Right. And when we proved that this is homotopy to the wedge of spheres, okay, we didn't use the EL-Shallable, we used the Morse matching, okay? We used the Morse matching and we proved the order complex is the homotopy to the wedge of spheres, okay? And the final lemma for this talk is if you have the Simplicial map pi to the p such that if for the all the x's in the poset p, the inverse emails, which is greater than or equals to x, is contractible, then we may say this simplicial is the order complex of the P. Okay, this is Coulomb 5 lemma in 1978.
What is gamma? What is P?
Okay.
These are simplicial
Simplex, yes, and this is the poset. For any simplex.
Simplicial complex. And a poset.
Poset. Okay. So here you have the simplicial complex here, and for the poset, you have the natural map. This is ordered set partition, and this pointed set partition doesn't have the order. So if you don't, okay, if you don't have the order for the ordered set partitions, you may have the just pointed set partition. Okay, and if you have the sum x here, we have some cones. Okay, and inverse emails of this is still, if you think the orders complex for the inverse image of this is again the cone we proved, so it's contractible. Okay, for any x in the poset P, the inverse image was the cone, so it is contractible. So these theorems we had for this delta C, okay, you may have the same story for your pi C pointed set partition. Okay, this is the wedge of spills of these numbers and the dimension K2. And the next the group action is not the natural, but we gave the some triangulars for each basis. So if we have the basis for the homology groups, so you may say the same things for the group actions for your homology group also. So we are done here. Okay. Any questions?